Root mean squared error is the industry standard error metric for regression models in data science. It's great for expressing, in terms of the units of your measurements, how far off you are. But what if those units are meaningless to you? What if you don't know how good or bad an RMSE of $50 is? $50 could be very small or very large error depending on the shape and scale of your data. Of course, you could take a quick glance through the data, but learning the shape of data is a manual process, and even if you become familiarized with it, you'll then have to explain that to someone else, and that whole process takes too much time. There's a better measure of error that solves all these problems, and that's relative RMSE. The problem, and the reason I'm making this video, is that no one really agrees on how to calculate relative RMSE. There's only one YouTube video on it, and that video provides one formula for calculating it. There's a couple of Stack Exchange posts on the topic, but they provide different formulas. And there's a Wikipedia article and an Analytics Video article on the topic, and they all present different formulas. And when you ask ChatGPT, it just says that there are several different ways to calculate it, so I set out to test every single one of them and discover the best one. At its core, the idea of relative RMSE is to divide the RMSE by some value. Obviously, since the denominator is some constant, it doesn't change the proportion of error between columns. This isn't a project to find the most accurate metric because they're all based on the RMSE. This is a project to find the most useful metric. So I created a dataset with several test columns. The first column is the control column, and it's full of random numbers between 1 and 100. Then there's the near control column, which is a randomized variation of the control column within a range of 5. Basically, a value between -5 and 5 was added to the control column. Then there's the null model column, which is equal to the average of the control column. The half control column is a value exactly between the control column and the null model column, which might be where a mediocre prediction model lands. And lastly, there's the terrible column, which is full of values between 1 and 10. Then I coded up all of the relative RMSE calculations as functions and got about to testing them all. I tested each column's error against the control column, and the resulting dataset looks like this. Obviously, testing control against control will produce an error of 0 at all times. The more interesting thing to check is the range of values and the readability of that range. Most of these have seemingly random ranges that aren't useful for abstracting out a generalized rule. I do want to talk about one that has some foundation in the literature base, though: normalization by mean. According to this screenshot of the paper that I found on Stack Exchange, there's an established range of quality, where being 10% or below is great, and being above 30% is very poor. I went to read the full paper, and yeah, it doesn't really elaborate. But it does have a footnote, which leads to this paper, which unfortunately is locked behind a paywall. But anyways, this theory lines up with what I was seeing from my test. The near control error is under 10%, and the null model is well over the 30% threshold for being bad. The other one that caught my eye is normalization by standard deviation, which also shows up as normalization by the null model. I'll leave that as an exercise to the viewer to work out why that is. Anyways, this method always has the null model's error be 1 and the half null model's error be 0.5. This means that it's very simple to tell if your model is better or worse than the null model. Greater than 1 is worse, less than 1 is better. The other methods are potentially interesting, but not as useful since the errors for null model and half null model are seemingly random decimal values. The last thing I want to discuss is root mean squared relative error, or RMSRE. This method is discussed as an alternative to relative RMSE, but it's actually mathematically different, since it relativizes values before they are squared, averaged, and then square rooted. But that's a topic for a different video. For now, we've determined the best error method among the many variations of relative RMSE, dividing the RMSE by the standard deviation of the data, which produces a very straightforward 0 for perfect accuracy and a 1 for the null model's accuracy. To summarize, RMSE is limiting because it's expressed in terms of context-specific units, and if we need to assess a model's accuracy but don't have the context, relative RMSE is the best way to do that. Of the many formulas for calculating relative RMSE, the simplest and most explainable is normalization by standard deviation. If you'd like to explore this topic further, you can grab the source code from this video from my GitHub page linked below, and if you have any insights on this topic, I'd love to hear from you in the comments section.